first in-person talk, so it's a little strange for the last 2 years. So it's a little strange to take off my mask and be here in person. But thank you for having me. It is an honor to be here as a Patinsky Fellow. And I certainly enjoyed the last week at Peyton Hall, and very glad I have 2 more to meet with as many of you as possible. So let's jump right in. I'll try to answer some of your questions on is lensing low. So weak lensing is one of our most powerful cosmological probes. It has immense potential to map the dark matter concentrations, to be used as a tool of galaxy formation on small scales, and to probe the expansion history of the universe, getting at dark energy. Now, I'm very lucky that I did my PhD when the data in this field was just about to boom. So I think since back then, with the end of a survey called CFHT Lens, right before I started my PhD, there were hints that perhaps this probe could tell us some interesting things about our standard model. And now we have a lot more data to answer that question. So this is the breakdown of my talk. First, I'll explain what we're after, which is this end-to-end test of the standard cosmological model, lambda CDM, when we compare our large-scale structure results to those from the CMB. Now, to do this test, we call our analysis the 3 times 2 points, and it's a joint analysis of weak lensing and galaxy clustering. And so I'll summarize how this works, but I'll focus most of the talk on the lensing side, cosmic shear. I'll introduce the best lensing data set on the market for now, and that's the dark energy survey. And earlier this year, we delivered the leading lensing cosmology results. So I'll present those. And I wanted to highlight some of the methods that we use in our analysis, because we did our very best to deliver robust cosmology. And because of the precision that DES gives us, in many cases, we had to build new methods to be able to handle that statistical power. And I think that these will be important going forward. So I'll demonstrate how we overcame what we're going to call usual suspects for lensing, or the main hurdles faced by lensing cosmology, and how we overcame them with the DES approach. And finally, on the eve of surveys like Rubin and Roman and Euclid, I'll give some outlook on how we can move forward. So measurements from the CMB reveal a map of density and temperature fluctuations measured from the early universe. And a snippet of this map is shown in the bottom left here, as measured by the Planck Satellite. Now, this experiment represents the gold standard of cosmological precision. Its measurements of the matter power spectrum are an exquisite fit to our lambda CDM model. And that includes constraints on the AS parameter, or the amplitude of primordial density fluctuations. Now, the expansion of the universe marched on, those fluctuations cooled and expanded, and seeded the large-scale structure that we observe today. So on the right-hand side, you can see a snippet of the large-scale structure created in a simulation at SLAC, and you can see that pattern already there. And from this late-time universe, we measure a slightly different parameter, the amplitude of mass fluctuations today, or sigma 8. Now, weak lensing and clustering observations like what we make in DES are excellent for probing this current era, the one dominated by dark energy. So they measure a universe that looks very different to the one that the Planck satellite looked at. So it's not the imprint of very tiny density fluctuations, but large density fluctuations in an accelerating universe. And you can see already that when we compare our observations to the same model that's so well measured by the CMB, we create quite a beautiful end-to-end test. And it asks the question, can we use the same picture that fits the seeds of our universe to describe the vast structures that formed billions of years later? And so we're comparing our measurements of the late-time universe of galaxies and large-scale structure to the same model that the CMB measures so well. Now, as Jay alluded to, and as you know, it's a particularly intriguing time in cosmology. There are growing data sets, and so we see slight discrepancies cropping up, or tensions to varying degrees of significance. And that depends on who you ask or how significant these tensions are. But finally, we have the statistical power to be able to distinguish between what might be a statistical fluke or a real tension. And then the next step is to dig into whether this tension is something that needs new physics or something, some new systematic in our data. Now, of course, measurements of the Hubble constant have gotten quite some attention with their 3 to 5 sigma discrepancies. But less significant and nonetheless intriguing and seemingly not going away are tensions in the measurements of the lensing amplitude compared to the CMB. So let's just take a step back. What is weak lensing? Well, we observe the distribution of foreground massive objects to be spatially clustered. And then at the same time, their presence distorts the fabric of the universe so that when we look at background galaxies, their images appear lensed or distorted or shared. And that's because their light path gets bent due to the distortions in the large scale, in the fabric of the universe, thanks to the large scale structure. And galaxies whose light travel past the same structures in the universe, like these two on the left-hand side here, they acquire coherent distortions or alignments. So we measure a correlation between their shares. Now, these two observations, the clustering and the lensing, were the foundation of our cosmology analysis. And on the next slide, I'll just say that in a little bit of a different way. So here we're considering simulation volume. And light from the background yellow galaxies travels through the large scale structure to the image plane on the right-hand side. And the observed shapes in the image plane appear lensed and shared. And statistical measurements of their correlations tell us about that large scale structure that the light passed through. For the foreground red galaxies, they trace the web in the simulation box, or the underlying dark matter. And so a measure of their spatial distribution also tells us about that large scale structure. Even simply plotting the positions of large scale structure galaxies, like we did here for 2DF lens in the past, you can see the clustering of galaxies that we want to measure in our correlation functions. So we have two fields. There's a density field in the foreground and a shear field in the background. And for any field with a mean zero, like these two, a simple way to quantify the fluctuations is to measure the 2-point correlation functions. Now, to compute the 2-point correlation function for weak lensing, you need from your galaxies their positions and also a measure of their shapes, so the ellipticities, which we quantify in this 2-component ellipticity. And we compute the measurements between pairs of shapes as a function of their angular separation on the sky. And that gives us psi plus and psi minus, the shared 2-point correlation functions. Now, on the other hand, we compute the clustering correlation functions using the positions of the foreground galaxies, the position-position correlation. And that gives you W theta. Now, to model these 2-point functions, we need to be able to estimate their redshifts. So we measure the redshift distribution of our ensemble of galaxies, not a redshift per galaxy in DES. And I should also say that in reality, we don't just have one source sample and one lens sample. As I tried to indicate on the top there, we do our analysis tomographically. So we take our observed volume and we slice it up in redshift along the line of sight. And that gives us these redshift bins. And that lets us boost signal to noise. So we're not just measuring the correlation functions between all of the galaxies, but between one bin of galaxies with itself or with other bins in the volume. And doing this, as I said, it boosts signal to noise, but it also allows us to see how structure has evolved with redshift and get a dark energy. And we can directly relate these signals to lambda CDM, to our cosmological model, and lensing is particularly sensitive to omega matter, the amount of matter, and sigma 8, or the clumpiness of that matter. And as you can see on the right here, it's most sensitive to a combination of these two parameters. So this S8 parameter, which is a combination of omega matter and sigma 8. And this will continuously come up for the rest of the talk because this is the derived parameter that lensing is most sensitive to. Now, the cosmological workhorse for DES is this 3 times 2 point, very inventively, because we take 3 2-point functions and combine them. So there's the shape correlation function, and that's cosmic share. That's really the meat of the analysis. And then there's position of the lenses, galaxy clustering, and the cross correlation of the two, which we call galaxy-galaxy lensing. And that ties the galaxies to the underlying dark matter distribution. And you can also see on the right that cosmic share is slightly degenerate with what we call it slightly has a different degeneracy in that parameter space with what we call 2 by 2 point. So 2 by 2 is the combination of galaxy clustering and galaxy lensing, or just the other two that we're not going to focus on so much in this talk. But this kind of demonstrates why we combine them. They have slightly different degeneracies, and so you can break those. But more important than that is the fact that when we do a joint analysis, it allows us to self-calibrate the nuisance parameters or the systematics that hinder any one of these on their own. And so that it really helps us to maximize on the cosmological information and is quite powerful. So right now, the Dark Energy Survey provides the largest weak lensing data set. It was a 6-year survey. We just finished collecting data last year. I was lucky enough to do the second to last observing run a couple of years ago on the Blanco telescope. And the goal of the survey is to be able to constrain the dark energy equation of state using not just weak lensing and large scale structure, but also supernova, cluster counts, PAO. Now, in this talk, I'm going to focus on constraints in lambda CDM, but there is ongoing work to be able to constrain extensions to the standard model. And so in the end, we have this 5,000 square degree footprint on the sky, which is very nice to look at. And some of us even made a puzzle out of this, if anybody's interested. And we use a few photometric filters with a 3 square degree field of view camera. And we use this wide, deep survey strategy. So we have just a few fields with very deep information, very deep observations that's carefully chosen to overlap key data sets on the sky. And it really helps us to understand the data in our survey. And I'll come back to that later. Now you can do other neat things with this state-of-the-art data set. If you've lost your Tesla Roadster, it comes in pretty handy. Or if you're not quite sure if there was an earthquake the night before, DES can also help you out if you're on Ceres Lulu. But really what we're after is the weak lensing data. Now, DES aren't the only people in the business. So there's the ESO kilo degree survey with their footprints shown here in blue. I did my PhD as a core member of this team, helping to build the data that we use in our cosmology analyses, and very close collaborators with them still. And of course, you're all familiar with HSC, with key members of their team based here. So that's shown, the year 1 footprint is shown in orange. But the key point is don't be fooled by the smaller areas. That's not all that counts in this field. HSC boasts the most beautiful, deep, and highly resolved data, giving many, many more galaxies per square degree. And I've heard since I've been here that they're almost finished with their observations, racking up more than 1,000 square degrees. And KIDS also has more than 1,000 square degrees. In between in, well, slightly similar depths to DES, but key is that it has excellent wavelength coverage. So this sounds like a small thing, but actually it's extremely important because we have to estimate photometric redshifts. Now, our teams work independently. We have very different data and different pipelines, and we all do our analyses blindly. So we don't know the answer until we're finished. And it's very compelling that we've all found pretty much the same thing. So this is the weak lensing stage before the DES year 3 results. And I'm just showing some of the recent key results at that time from those 3 surveys in 2020. And so we're comparing here the constrained value of S8 as measured by the Planck experiment, that yellow shaded band. And then the different data points are all the different lensing surveys. Again, KIDS in blue, HSC in red, and DES year 1 in green. And the key thing here is that none of these data points disagree with each other to any real significance on their own. And in that way, the lensing tension is different to the Hubble tension. But there is a persistent trend here because each of these measurements sits somewhere between 1 and 3 sigma low compared to Planck CMB.
But I mean, the different points are not statistically independent from each other. I mean, many of them use the same data.
Yeah, so there are correlations, have overlapping footprints. I'll get to that by the end of the talk. And some methods are similar. So caution against trying to combine these by eye. But it is true that the lowness exists for almost every weak lensing data set to date. But weak lensing has always been challenging. The data is particularly hard to wrangle with, and I think only now that we've started to see the same results from 3 surveys at the same time and hone our methods is the evidence building up that there really is something here. And I should say as well that at the bottom are when you combine with clustering, and this can increase your tension or keep it the same. I'll say a bit more on that later on. Now, maybe to state the obvious, there are 3 options for an explanation here. It's intriguing to think that this suggests some kind of crack in lambda CDM, but before we get there, it could be that there are systematics in both types of measurements. So as lensing is a relatively new field, the signal is very tiny and the Scher observations are pretty difficult to make. It's fair to say that we knew our results would be under scrutiny. and that it was our responsibility in DES with the statistical power to ensure that our systematics were under meticulous control before we declared some kind of exciting finding. And after years of work, we added a new measurement to that plot this year with the DES Year 3 data. So the Year 3 survey spans the full area. So compared to the final survey, compared to the Year 6 that we have in the end, it's half the depth. So it goes out to a mean redshift of about 0.6. And in the end, after we do all our catalogue selections, we ended up with more than 100 million source galaxies. And that's 3 to 4 times the number compared to DES Year 1 or the next leading recleansing experiment. And this really is unprecedented precision for a recleansing survey. And so we knew we had to take extra care. And I'll try and show you a little bit what that pipeline looks like. So this slide is meant to be overwhelming. It is to convey that it is a pretty hefty roadmap to be able to deliver a validated and robust data set that we can do precision cosmology with, or any of the other countless analyses that benefit from the calibrated DES catalogues, which will be public in January. So here's just a top level overview of that very multifaceted process, and I'll orient you a little bit. There are images on the left-hand side, the wide images and the deep field images. There's data calibration in blue, all the different aspects of that. Then you get to your modeling in orange, and finally to cosmology parameters on the right. So my focus for Year 3 was on the blue, and then I led the cosmology results from Cosmic Share on the right-hand side. But it's important to say that each bubble kept a team in DES busy for a couple of years, and that's, I think, evidenced by the suite of papers that we published supporting our cosmology results. Now, it goes without saying that DS is really a huge team effort and work I couldn't do alone, especially coming from the much smaller kids survey. DS is really quite the machine. Our scientists are from all around the world with many supporting institutions. And I think that's really what it takes to do good science. It's a lot of work to be able to build a team from a diverse set of people with an inclusive and a supportive environment. Now here's a photo of the main Year 3 team. I usually show this photo taken on unblinding day, which was the day that everybody got to see our results, including us. And that was coincidentally on the same day as US elections. But I decided to be kinder to myself and my colleagues and show this collage where we all look significantly more relaxed and refreshed rather than the screenshot on that day. And finally, here are our results. So I've added, these are the Cosmic Share results. I've added 2 more data points to the compilation on the left-hand side. These are both the Cosmic Share results, but the bottom one has slightly more aggressive analysis choices. And on the right-hand side, you can see the 2D constraints, so omega matter on the X and that S8 parameter on the right. DES Cosmic Share is in green, and in orange are the Planck 2020 results. They look different to what you might normally see, and that's because in DES, we make the choice to reanalyze Planck in DES choices, which includes freeing the neutrino mass. So usually Planck fixes that to the 0.606, to the minimum mass allowed by oscillation experiments, but in DES, we free it. And so that inflates the Planck contour a little bit and changes the shape. Now, before seeing our results early on, many years ago, we pre-decided what statistics we would use to decide how to quantify consistency and the threshold for consistency. And we decided that we'd have a p-value defined greater than 1%, and that would point us to inconsistency or consistency. And so formally, what we find is that our DES Cosmic Share results are consistent with the Planck value. It's about a 2 sigma level and a p-value of about 0.04. That's true, that holds true when we look at the full parameter space and a suspiciousness, or just that shift in the S8 parameter. And that of course is tantalizing, it is intriguing, and honestly, for the most part, it's frustrating because we spent so long adding a new data set to this plot, the most powerful data set we could do. And in the end, it is consistent with Planck on its own, but clearly continues this trend that all the lensing data sets are 2 sigma low compared to Planck, 2 to 3 sigma low. And I think that does point to an S8 tension.
And does that whole left-hand plot include varying neutrino mass?
Only DES varies the neutrino mass there, and Planck does not. The Planck constraint I put there is the real Planck constraint. I should also mention that I also put a reanalysis of the Planck data from a team at Cambridge, well, 2 people at Cambridge, which they find a slightly lower value of S8 and tighter error bars, but it doesn't resolve the tension. Now we also measured these other 2 points correlation functions, galaxy clustering and galaxy lensing. And when you throw those in, you get the blue constraints shown here. So one of our requirements to unblind, well, a result and a requirement on the same day, is that we had to show that these were consistent before we could look at our 3 × 2 point results. And the clustering in this case kind of reduces the gap between Planck and cosmology on its own slightly, but it's still at the 1.5 sigma level. So again, no decisive evidence for a discrepancy from DESE3 on its own with Planck. But when we consider the cosmic share measurements, that is what seems to be driving things low. So given the cosmic share, I've told you how tricky it is to make, one might ask, could the lensing measurements be wrong? Now, I will make this skepticism easy for you and arm you with what I think are the 4 main challenges in a cosmic share analysis.
Nita has a question.
Sure, sorry.
Yeah, hi Alex. A quick question on the sigma 8. Yeah, on that plot. So because Planck gets a higher omega matter than many of the large scale structure observation, the S8 includes the omega matter in it. So that means that their sigma 8 is consistent with the lensing measurements?
That's a good question. I should have put the 3 panel plot here of omega matter sigma 8 and S8. It does seem to be, I guess I'm not sure which large scale structure measurements you say Planck is offset from. I think the set that we showed in our papers, omega matter from other experiments, is pretty consistent. When we look at which parameter is doing the pulling, it is just the combination of the 2. It is this S8 parameter. It's not starkly omega matter or sigma 8.
But I have another question. This is Jerry Ostriker. Are you looking at the same wavelengths? Because it could be that if the slope of the power spectrum isn't exactly what lambda CDM has, Planck is measuring at a longer wavelength than you are measuring. Are they looking at the same wavelengths?
I think those kinds of things, I don't know the specific answer to that question, to be honest, but I know that there is a group who's been digging very thoroughly into these Planck measurements and trying to see how you can move Planck low. And nothing gives. The Planck data points are just so well fit to the power spectrum that it is very hard to move Planck lower. And as you'll see, similarly for the lensing measurements. Let's go to the main contenders, and then maybe you'll have more questions. So these are what I would worry about in my cosmic share analysis, your suspects for today. And I will tell you why I think that they are robust from the DESE3 analysis. So first on the calibration side, central to a weak lensing analysis is some comprehensive understanding of the data. So on paper, this probe is extremely powerful, but in practice, it is increasingly difficult to be able to extract the lensing signal from the images to the required precision, so to match the statistical power. And specifically, you have to validate, well, you have to measure, you have to calibrate, and then you have to validate your redshifts and your shares. So starting with the redshifts, we need to estimate photometric redshifts for our ensemble of galaxies. And this is the most popular target for lensing skeptics over the last few years. And so when I moved to DES from kids, it was the part of the analysis that I decided to spend most of my time on for year 3. Now, why is it so challenging? Why is it so scrutinized? Well, it's because photometric surveys don't have nice spectra, is the easy answer. So if I had these black lines shown here, I could see that I have 2 types of galaxies at 2 different redshifts. If I only have observations in a small number of bands, like RIZ for the case of DES, these redshifts are now indistinguishable. So with these limited observations, there's this huge degeneracy between galaxy redshift and galaxy type that we need to understand. Now for the DESE3 analysis, we built an entirely new framework. So we started from scratch and we prioritized 4 key aspects. The foundation for all this is the deep wide survey strategy. So on top of that, we consider the training sample, the method, and the uncertainty. So for photoses, you need to understand your color redshift relation. And we used a subset of our data where we had better wavelength coverage. So these are the dense deep fields that I mentioned before. And these are chosen to overlap with near-infrared data, specifically from ultravista and from video. And in the end, in those deep fields, we therefore have 9 bands of data, and it makes understanding that color redshift type a lot easier. Now, you can't get this 9-band data over the entire DES footprint. It really is the best feature of the kids survey that they do have overlapping near-infrared data. But to be honest, it's not a luxury that we can expect to have in the future. And so I think this method that we built in DES helps us get around that, and it's going to be really powerful going forward. So we can attain this information for a subset and use these deep fields like a stepping stone between external data where you have very small area but well understood redshifts, and then your DES data over 5,000 square degrees, which has redshift core information. And so we're using, well, we use an overlapping part of the data where we have both deep and wide to make a kind of truth table. So in the deep fields, we can decode these redshift type degeneracies in that privileged 9-band color space, and then apply that understanding to our wide field. Now, to estimate the color redshifts, that relationship, we use a self-organizing map. So this is just a fancy machine learning way of compartmentalizing your galaxies. So the idea is that all of the galaxies that look very, very similar in color and magnitude, we put them in the same compartment, and then they get assigned the same redshift. Now we have 2 SOMs, or self-organizing maps. There's the one for the deep field, which is very high resolution because we have so many colors, and then there's the wide field, and we can map between the 2 of them. An important point is that you have to mitigate any biases in that color redshift relation. And so that's point number 2 here. And this was something that was heavily debated at the time that I moved between the collaborations and within the lensing community on whether you should be using a spectroscopic training sample or a narrowband photometric training sample. And the debate is because really neither of them are perfect. The spectroscopic ones never look like the lensing data. They have huge selection effects. And the photometric ones can be inherently biased. So I wanted to ensure that we were robust to this choice, and we created this combined sample that let us maximize on the spectroscopic information, but still maintain completeness. Point 3 is talks about the method. So traditionally, weak lensing analyses use multiple methods, which is really great, and they use them as a consistency check, like, okay, these look the same, we're doing a good job. In DES, we wanted to go beyond that and really combine all the information. So we had 3 different methods, one that used cross-correlation with clustering, one that used something called shear ratios, and then the self-organizing maps. We assessed the consistency between their likelihoods, and that was another one of the requirements to unblind our data. And then we combined to be able to maximally constrain the uncertainties on that redshift information in our MCMC analysis. And then the final point here on uncertainties is quite a technical detail, but it is important. The traditional approach is that in lensing, you only need to know the mean redshift of your bin. You don't care about the shape of it so much. So the uncertainty in your analysis, the prior that you use in your MCMC analysis is usually just a shift on that mean. Now in DS, we wondered if we had to now worry about the shape of the redshifts. So with this fancy method, we created an ensemble of realizations. So we had 6,000 redshift distributions that all could be plausible, and the span of these ensembles, the span of this ensemble reflected all the sources of uncertainty that we could think to put into them. And we could sample over these realizations in our MCMC. Now, in the end, our calibration was very well received, even by our harshest critics, and it's now being adopted by other teams. So I would say that redshift calibration cannot be the cause of the S8 tension. Turning to shape measurement. Now, our weak lensing data isn't the beautiful spiral galaxies that you imagine, or even the beautiful spiral galaxies that HSC probably sees, but more like these fuzzy blobs on the right-hand side here. So this picturesque spiral first passes through large-scale structure and gets that nice cosmic shear signal that we really want, and that's a 1% effect. And then it carries that signal all the way with it to Earth. Now we have to detect that 1% signal, except that's quite hard when the Earth's atmosphere smears and distorts that image even further. That happens some more in the telescope, but it gets pixelated by the camera, and then there's noise. And so really what we end up with is something more like the blob on the right-hand side, and I'd say that's probably a pretty good galaxy in DES. So for the year 3 analysis, I coordinated the team that, that accounts for the point spread function, so how much that atmosphere is ruining our images, and validates the share catalog so that the team could use it for cosmology. And there are a few points that where we built on year 1, we used new point spread function modeling. This was actually really turned out to be really important. We were able to have a much better control on that for compared to year 1. We extended the suite of tests that we did, and in the end, we had this sample of 100 million galaxies. That's not the end of the challenge, though, for shear measurements, because there's blending or crowded fields. So one blurry blob we think we can handle pretty well now, but when you have 5 blurry blobs that sit on top of each other and they're all at different redshifts, the calibration challenge is a little harder. So I advised another graduate student. I didn't mention Justin Miles in the redshift slide. Justin Miles is a graduate student who I had the absolute pleasure of advising at Stanford. He is fantastic, and he led the redshift analysis in DS. Jamie is another student who I've been lucky enough to co-advise with Daniel Gruen, and she worked on the shear calibration. So we tested the realism of the image simulations that Des built, and then we applied the redshift method to the image simulations. And in that way, we could look at the effects of blending in each of our redshift bins, and therefore account for it and model it in our cosmology analysis. And in the end, what we had is this cosmic share S8 result that was absolutely robust to any dial that we could think to turn in our data calibration. We could use an entirely different training sample for the redshifts, and our results were stable. We could take away one of the methods and it held up. We could throw in an additional share error in case we missed something, and the results still held. And so I think this is the most rewarding plot that I will likely ever make in my life. It took 3 years, but our S8 results are robust to our data calibration. So if you believe me on the data calibration, you might want to throw stones at the modeling of our systematics. And these arise simply because galaxies are complicated. They aren't just the fuzzy blobs that we can think about in our calibration. So problem number 1 is that they can be intrinsically aligned. So that would break down the weak lensing assumption that the correlation that we observe is solely due to lensing, solely due to the large scale structure. And so we need to ensure that we model the intrinsic alignments so that they're not masking some lensing signal. And then secondly, that galaxies have complex baryonic processes which modify the matter power spectrum on small scales. And I think the key here is that we need to make sure that we're modeling the measurements in a way that's flexible enough to encompass the fact that we don't really understand the intrinsic alignments and baryonic effects. There's a huge amount of uncertainty there. And we need to do that without looking at the data. So a priori prove that the modeling is rigorous enough to mitigate any potential biases. So to get across the point of baryonic effects, I'll just show you our cosmic share measurements. So just to orient you a little bit, there are two statistics, psi plus and psi minus. Those give you the 2 triangles. 4 redshift bins, and you cross-correlate each bin with itself and with each other. I've blown up one bin, one pair there. And so you're looking at psi plus, and on the x-axis is the angular separation, on the y-axis is the amount of lensing scaled by that theta. Black data points are our measurements, green line is our best fit model, and the yellow shaded region is the Y1 uncertainty, just to see how much statistical power we gained compared to year 1. And these are the highest signal to noise measurements from cosmic share to date. Now the takeaway here is that this is a very large data vector, lots of data points in our measurements, but we get a good fit to the data with the green line fitting the black measurements. And the lower panels are the residuals, the difference between the measurements and the models. And what I really want you to notice is those blue shaded regions. So these are our scale cuts. So it is a bit of a disastrous situation in lensing where we throw away anything that's blue. So we know that AGN in galaxies blows baryons outwards, but there's a large uncertainty on the amount or the extent of that feedback and how it impacts our measurements. And our ambiguity is well illustrated. It's a little blurry, but this plot in the bottom right, where you're looking at a compilation of hydrosims. And it's the ratio of the hydrosim power spectrum to the dark matter only power spectrum. And you can see that there's suppression on small scales or large K scales. And even on mildly nonlinear scales, there's a huge scatter between what these simulations predict for baryonic effects. So it's safe to say that we don't precisely know how to model baryonic feedback in our measurements. That's why we have the blue regions. So we take each simulation and we model how it would impact our cosmic share measurements. and throw away the data until the level of bias is negligible. So in DS, we pick the most extreme but realistic simulation. And so therefore, we're picking the maximal amount of feedback that we think the universe could have, or our galaxies could have. And we make sure, we do that to make sure we're conservative as possible in our analysis. So these scale cuts are really on the conservative side. And you can see that for the measurements that we do use in white here, the model is an extremely good fit to the data. So I think we felt assured that baryons were unlikely to cause the S8 tension. Yeah, I see hands.
So as you noted, we don't really understand the feedback very well. So I guess how confident are you that the most extreme of this particular set of simulations is actually a bounding result?
Yeah, that's an excellent question. It's what I'm spending my time working on now. There's a huge range of simulations. I think it's a shared belief that Illustris, which is the yellow one there, is probably too extreme when you consider constraints from other experiments. So we just picked the next extreme one. It could be that we've missed something and baryon feedback is way more extreme than any of these predict, I think, but given external constraints, that seems unlikely. Yeah. Jamor, you want to go first?
Why do these effects show up more strongly in psi minus?
Oh, so psi minus is just like the one that gets all the systematics because you're subtracting one from another. So it's a smaller signal and everything's worse in psi minus. We usually throw away lots more.
But maybe it's a follow-up question. Why would you not cut at the same scale all the data?
That's a good point. I guess we played with many different ways of doing these scale cuts, and we wanted to be able to maximize on signal to noise and minimize on the bias. And some redshifts, these different hydrosims predict different redshift dependence of their baryonic effects. And so that's why we take each one and model how it would look in our measurements. I think I have that part in my exercise, and then decide to the bins that keep the most signal to noise essentially and minimize the others.
So I'm struck though that despite cutting, the model seems to go through the data. So is that a good thing? If you had chosen a different hydro simulation, would you get discrepancies? How should we interpret that?
Yeah, that's a good point as well. And it's, I find it particularly intriguing, but also exciting because maybe baryons aren't quite as extreme. So just to be clear, we don't tailor our model to a specific simulation. We just cut out to be able to satisfy the most extreme case. So it could be that our data is preferring any one of these simulations that are less extreme than ours. So if we tried to use a different simulation to do that, it would just lift our scale or reduce our scale cuts, but it doesn't change the fit of the model. But it is very interesting that the model is pretty well fit on small scales as well, on the scales that we throw away.
Maybe to ask it another way, how much do you need to change the effect of the baryonic or the feedback in order to get everything to agree with Planck, for example?
Yeah, this is something that I've been looking into and we are currently writing up. You have to make a pretty extreme case for baryonic effects to be able to fit everything. Mm-hmm. And too extreme to be able to satisfy.
Yeah.
But I think what I'm going to ask follows from everything else. But so if you change the scale on which you do the cut, given the fact that the model still goes through the data on smaller scales, it doesn't really change your conclusions. Is that correct?
Yeah, so that's not something that we published, but I have looked at that. And if you just do your analysis, not throwing away any scales, we get much, much tighter results as you would expect. And they don't move that much. They shift the lower S8 slightly, but they're surprisingly stable. Okay, baryons, I'd say unlikely to cause the S8 tension. Finally, to intrinsic alignments, the last suspect. I won't go too far into the details here. And so what I've drawn on the left-hand side is really a toy model, but there are, and you can describe your cosmic ray measurement as a GG term. And for intrinsic alignments, there are GI terms and II terms. And they are in parts due to the tidal alignments, due to galaxies residing in similar regions of large scale structure and interacting locally. So their alignment, if not modeled carefully, looks like a cosmic share signal. Now, in DS, we use a more flexible intrinsic alignment than previous surveys have used. So we use this tidal alignment and tidal talking model, or the TAT model, we call it in DS, and it's a nonlinear perturbative prescription. Now, previous analyses have assumed the NLA model, or the nonlinear alignment model, which models intrinsic alignments as linear in the tidal field with a nonlinear power spectrum. TAT is just a super space to this model. So it's more conservative than the NLA model, and it doesn't only include that tidal alignment term, but it also includes the next two leading order terms. So that's the density weighting and the tidal talking. And theoretically, these terms are well motivated, but observationally less studied. Now, this is not the choice that I wanted to end up with, this conservative model, obviously, because it reduces our constraining power. But we don't look at our data. We do all our testing in a synthetic framework. And we found, before we looked at our data, we found that we could not ignore the fact that there could be scenarios where the intrinsic alignments were complex and extreme enough that we would require this more conservative model. So we had to go with the more conservative approach. So there were some instances where the NLA model could fail. Now, in the end, when we unblinded our results, so again, I'm showing that the fiducial result is in green here, and different variations in the IA model, simpler IA models in the other contours. So once we unblinded, we could look at the difference or how this choice impacted our results. And surprisingly, you could see that, well, to my surprise, we could see that the NLA model, either the 2-parameter NLA model in blue or the 1-parameter, even more aggressive in yellow, give consistent results within 0.5 sigma with a much tighter error bar. Even no intrinsic alignments show in red. So if we decide that we're not going to model this, which is absolutely wrong, there is evidence for intrinsic alignments, it doesn't shift our results very much. So our essay results are also stable to the intrinsic alignment modeling. And I think, if anything, we were over-conservative here, and we're thinking about how to be able to make this decision in the next time we do this.
So are you actually measuring an intrinsic alignment signal, or are you just putting a limit on it?
We measure the parameter. So in the signal parameter model, it's an intrinsic alignment parameter, A, and it comes up very small, which is consistent with kids. In the DESIR-1 analysis, this parameter had a huge error bar, and so it could be that it was bigger and you would require a conservative model.
It's small but non-zero?
Small but non-zero and positive, yeah.
Thank you.
Yeah.
Is this consistent with like prediction from hydrodynamic simulations for the? Yeah,
so it is consistent with those, but we don't actually have a lot of information about intrinsic alignment measurement, like direct measurements or predictions from simulations. So they do come up, I guess. There's DES bias knowledge. There was an analysis earlier this year by Simon Samaroff who looked at hydrosims, measuring intrinsic alignments in hydrosims. Again, there's a huge range in the hydrosims, but when we compare to direct measurements from the data, that's what informed our models. But there is very little information, so we have to be quite conservative in our modeling to account for that uncertainty. And finally, I want to mention the last thing in this suspect list is blinding. I keep mentioning this blinding. You could see quite how many choices and dials we turn in our analysis along the way. And so all the lending surveys, it's common now to blind our analysis. In year 3, we went pretty rigorous with this. So we didn't just avoid looking at the parameter constraints compared to Planck or compared to DESIR-1. But we decided to have the philosophy that we could make no decision based on data. So for example, in our modeling, we couldn't see that the NLA model gives an even better chi-square than our TAT model. So in anything, it's more aggressive, but as good a fit. So we couldn't see that and just pick the simpler model to get the most out of our data. We had to make absolute conservative choices. For example, we also couldn't look at the relative sizes of contours with analysis variations to make decisions. We couldn't look at the internal consistency of our 3 measurements until we were absolutely finished and got 250 people onto a call to look at it with us. So that you can imagine that this was the source of many, many nightmares for a long time. And looking back, I think it was a very extreme choice to blinding. I think it is something we're thinking about for year 6 because it makes you go a lot slower, but I think it adds to the robustness of our results in the end. So our cosmic share suspect list, it is hard to point fingers at something that is causing the assay tension. And it was necessary to develop the methods to be able to handle the precision from the DES data along the way. But in the end, our assay constraint is stable to the dials that we can think to turn right now in the data calibration or the modeling. where does that leave us when we consider the other independent surveys results? And now I've added 2 recent constraints this year from CMB lensing cross correlations, one with unwise and one with DESI imaging, and they also come out low. And so it is this intriguing puzzle of what is happening here. Why do all the measurements sit some 2 to 3 sigma low compared to Planck? And how do we pin this down? I just want to stress the point that Michael pointed to as well, that each of these teams make their informed analysis choices blindly, but there are different modeling choices in each of these data points and different calibration techniques. So combining them is really not trivial. It's not, you can't just average them together. So to me, the first next step to tackle that is to do a joint analysis. As one of the 2 people who are in both KIDS and DES, I'm working with a couple of the key members from each of the teams whose names I put there to do a very rapid joint analysis of KIDS and DES cosmic share. And so all we want to answer is not which analysis choice is best. We're leaving that off of the table and just asking, when we combine these 2 data sets, do we push over 3 sigma? That's really what we want to get to. Because KIDS and DES use different analysis choices, it means that we're having to do 2 results, one in KIDS pipeline and one in DES pipeline, essentially. The next step is to do it all again with DES year 6. So this time around, I'm coordinating the full weak lensing team, and our data grows in depth compared to year 3 to twice the depth. And so that jump is really streamlined with preparations for Rubin in terms of being able to handle deeper data and pushing out calibration methods. Now, you don't need to look at that. When you enter Peyton Hall and you turn right, there's that beautiful HSC floor-to-ceiling image, and you don't need to look at that for too long to see that deeper data is stunning, but brings with it its our calibration, our blending challenges will be absolutely pushed to a new level with HSC at maximum depth and with LSST. So for DES, that year 6 legacy survey is our last stepping stone before Rubin, which is quite literally on the horizon for DES. So this image that I keep showing is when you're standing at the Blanco telescope on Cerro Tololo, and 1 mountain over is Rubin under construction. So the progress that we make in DES, HSC, and KIDS is really just laying the foundation for the precision cosmology that we'll get in the next decade. And the last point I wanted to make for the last few minutes is, what else can we do other than getting more lensing data? So at the end of the year 3 analysis, I played this game, which is highly idealized, of what if we could do everything perfectly? What if we had no uncertainties? What's limiting us? So the green contour is our fiducial contour. If you switch off your redshift and your share uncertainties, you get the yellow contour, and there's no difference. So we can give ourselves in year 3 a pat on the back that we calibrated our data to sufficient precision so that it wasn't limiting our statistical power. And that really is, I think, a feat for weak lensing. I'm not sure we'll be in the same situation when we get to Rubin. Next, you can switch off your theory systematics, and that gives you your red data point. So that's now using full scales and no intrinsic alignment error. And these are all centered on each other. There are biases, but it's just looking at the power. So fixing the theoretical systematics gives us almost twice the S8 constraints. So it's much more powerful than what we've done. It is an idealized dream to be able to think that we do this with no uncertainty in any scenario. But what I wanted to point to is what's limiting us and where do we need to work. So we can see that the theoretical systematics are limiting the precision of lensing. So given that, now at my new position in Cambridge, I've decided to change tact, and this time around, while coordinating the year 6 analysis and the calibration, I'm spending my time on 2 ongoing projects that address these 2 main theory systematics, intrinsic alignments and baryons. And that means connecting with external data to learn what we can about these theoretical or astrophysical aspects. So we're connecting with CMB data from advanced ACT and spectroscopic data from DESI to improve our understanding. So what's missing? Well, we need more information on intrinsic alignments. So there are very few measurements of direct detections of intrinsic alignments. They do exist, and we know that that's a real thing. But what we want is these to higher precision so that we can split them up by galaxy properties and learn what the intrinsic alignments depend on. So we use this very conservative model for intrinsic alignments, as I said. But it doesn't use any information about our galaxies. It doesn't use the fact that we know their colors, we know their redshifts, we know lots of other properties about them. And so it's not a data-driven model, it's a theoretical model. For example, we've never actually detected intrinsic alignments of blue galaxies, only red galaxies, and blue galaxies actually dominate our weak lensing samples. So it'd be quite handy to be able to learn about these things. So in DESI, we're making, I mean, DESI will be fantastic. It's the new BOSS, if you like, a spectroscopic survey that switched on earlier this year, and it already has more data than BOSS. So while they'll do really nice BAO cosmology analysis, I will use their data to measure intrinsic alignments for different populations and try to inform our model choices. And finally, we're currently doing a joint analysis with kinetics and Zildovich information from advanced ACT. So using advanced ACT lensing and clustering data. Now the KSZ information maps the gas pressure around dark matter halos and it's proportional to gas density. And so it really helps us constrain that baryonic feedback and test against the simulations. And of course, this is not only interesting for galaxy formation, which is interesting in its own right, but hopefully in the future, we'll have more informed modeling choices, being able to pick a hydrosim that's best representing our universe, answer the question of what if it was more conservative, what if it was more aggressive feedback, and hopefully pin down some of our priors that we use in our MCMC. And with that, I'll leave you with our summary and take any questions. Yeah.
So it looks like when you had no intrinsic alignment, it really didn't make that much difference. So I'm curious why, how much you expect to get out of the further investigation of the intrinsic alignment from, baryonic simulations.
Yeah, that's a good question. So that is surprising to us as well. It's different to what we saw in DESI 1, where when you use no intrinsic alignment model, there was a significant bias. I think that it's because we see a very small intrinsic alignment amplitude. It's very near to zero, and that is what the kilodegree survey sees as well, interestingly. But because we have no measurements of, well, we don't have very good direct measurements of intrinsic alignments, we don't know what this looks like. And so we have to be as conservative as possible. So the way we made that decision was taking our year 1 constraint on the intrinsic alignment parameters, the maximal bounds of that, and it had a huge error bar, and injecting that into fake data, making fake measurements, and then analyzing that and seeing if NLA could recover the truth. And it could not, because there's this huge extent that's possible. So I think by using DESI and looking at the redshift dependence of these things, the color dependence, the luminosity dependence, what I hope is that, I think the first step will be an analysis that gains nothing in constraining power, because you will have many more parameters, but that you'll learn more about the properties and be able to, I don't know, maybe the future of cosmic share will be a red and a blue analysis, which is what's been done in the past. And that will help us switch off intrinsic alignment parameters for blue if we are convinced there's no IA there, and keep it on for the red. Yeah.
With DESI, how many different galaxy populations can you make? DESI is basically probing strong emission line galaxies. So you're probing probably the bluer ones that are hard to test. But they also have the weakest signal. So if you don't find anything there, does DESI actually allow you to go somewhat redder and to see when you start picking it up, or is it too blue for anything other than kind of the most bluest ones that we get in DS or other surveys?
Yeah, that's a good question as well. We're still pinning down what signal to noise we expect to get, not just because of the specific DESI samples, but what's the overlap with the lensing data, because we use lensing data to be able to constrain the IA, to be able to directly measure the IA. DESI has a bunch of different samples. They're ELGs, LRGs, and BGS is what I think I'm really after. And I think from the DESI year 1 data, our intrinsic alignment constraints probably won't be the most compelling, but as DESI grows and their data is growing so rapidly, we'll just continue repeating this when the decision is there. Yeah.
So in the baryonic simulation that you showed, it looks messy, but there is some order in it, in the sense that you can model these effects throughout all the simulation with 1 or 2 parameters. And my question is, does someone try now to fit the DES results using such parameterized baryonic effect models?
Yeah.
And in what direction does it go?
So there are a few different approaches and discussions on what's the best way to model baryonic effects. So you can use a halo model approach, a perturbation theory approach, a baryonification approach by Ora Schneider. which is who I'm working with to do this joint analysis. And that's, for example, that approach is a 7-parameter model. And so we're really trying to see, I guess you need a physically motivated model, but we also have limited precision. And what's key is that with the lensing data alone, so we tried this of just taking the cosmic share results, fixing the cosmology with the large scales and using the small scales to constrain, to tell us about that parameter and then compare that to the simulations. And we just, there isn't enough power in the cosmic share alone, even with the small scales, to distinguish between the simulations well. We do need external data. So there was a nice paper by Oral Snyder that pulled in X-rays and KSC, and that's what we're repeating for DES to try and have a better understanding.
Because what you said at the end with the factor of 2 reduction seems to suggest that there is enough constraining power.
Agreed. That's what I thought when I first made that plot, and that's why we did that quick thing of digging into it. That power does not go solely into the intrinsic alignment, into the baryons. I think it goes also into intrinsic alignments and other nuisance parameters. If we could pin those, if we could do it without intrinsic alignments, it'd be quite nice.
So would it be, given this thing of the baryons, would it be a benefit of doing HSC plus DES? Oh yeah, I mean there are scales that we think we can model well, as we've done our analysis with it. And so just by boosting the signal to noise on that will help you. It will just, there's a limit on how much you can get out of the data right now, unless you get to those small scales. But I mean, someone would want to use HSC data and do the same baryonic feedback game as I know that you are working on here. You could use that to learn about the baryons as well. Be quite powerful with its high number density. But then probably better if you included DS as well.
Oh yeah, for sure.
Yeah.
I think I'm kind of finished with doing any more papers with one data set alone, and just only going to use the combined results from now.
On Zoom data, I have a question.
Sure.
Yeah, thanks for a beautiful talk and beautiful work, Alex. A quick question on the comparison with Planck. Of course, the Planck values depend, they have a multi-parameter, so it's a mixture of all of the cosmological parameters together. So how does that relate, how does this value relate to the Hubble discrepancy? Because they get a different Hubble value.
Yeah, so I think that's a question that a very good question that I'm not an expert in, but I've seen lots of papers on the archive trying to connect these two tensions, if that's what you're alluding to, that Hubble, the H0 tension, the H0 parameter is low, as is the S8 parameter. I don't know the answer, to be honest. I'm sure someone else in this room has a more informed opinion on. I think people have speculated different solutions, like physical models that would attempt to alleviate both of these, and it is, I don't think I've seen a compelling one yet. Michael, do you?
Yes, you made passing reference to the challenge of Rubin Observatory going deeper, and the deblending problem gets more challenging. I wonder if you can say a little bit more about that and how we're going to tackle that, and we collectively are going to tackle that.
Well, I'm interested in learning from HSC.
And I guess a related question is, will Roman be useful for this at all in the deblending context and other ways?
Yeah. So I think we're going to have to pull in all the resources we can get and work together. So HSC will have tons of expertise on how they deal with blending, given that it's a much more challenging thing for their deep data. In DS, I don't think we can find a way to escape image simulations that are extremely complex and as realistic as possible. So for year 6, we are trialing 2 new shape measurement techniques, but already in year 3, we could see that correction factor, our shear calibration correction, and the uncertainty was almost entirely blending already. So we're doing as good as we think we can do in the absence of blending. In simulations, I think that the way we built our simulations in DS, there are lessons to be learned there, good lessons to be learned there. So we took out deep field galaxies, injected them into image simulations, ran the full redshift analysis on these simulations. And so I didn't show these plots, but the simulations are almost identical in the properties when we compare it to the data in terms of color properties, size, redshift distributions. We, by design, tailored them to our data. Of course, they still rely on on putting in everything you can think of. So one thing that we didn't put in, for example, was source clustering in the image simulations. And this is something that we got pretty strong feedback on from our colleagues and kids. And it was a valid point. It's something that we missed out in our simulations, or we didn't have the breadth to do. But luckily we got that before we put out our cosmology analysis, and we could use existing work that told us this would be a maximum this effect for Euclid. And that's why I said we did an analysis where we put in an additional shear uncertainty. That could be something we've missed, and showed that our results were still stable. But there are certainly lessons to be learned. I think one handy thing that I didn't talk about, that I looked into my PhD, is using the overlapping data from the lensing surveys to do consistency checks between them. And that's not just to say who's right, but to learn from the different properties that the data have that's good. And that exactly points to what I think will be the best way forward with LSST and Rubin and Euclid. It's the combination of them. They all have these really nice features. What together clearly is the best option.
Winwin has a question on Zoom.
Sure.
Oh yeah, thanks for the talk. I'm going to ask a very naive question. So for each galaxy, how do you represent its shape? What about, let's say, I saw that you draw ellipses as at the boundary of the galaxy, depending on the light profile. What if the galaxy is like clumpy in some wavelengths? How do you determine the boundary where the end of the galaxy and then the universe?
Yeah, that is a very well thought out question. You're paying close attention. So that ellipse is just for demonstration. We don't. I think that's the old way that's the way that DS used to do shape measurements, where you assume a model for your galaxy and fit that and get the shapes from that. For year 3, we use this measurement technique called meta-calibration. And that just takes your galaxy, it's model independent. So it takes your image and it stretches it in different directions and sees how it responds to an additional share. And from that, we get from every galaxy this share response, and use that to get an estimate on the share on the galaxy. So it's no longer this way of which incurs all kind of model biases of assuming the shape.
I see. Every pixel is being used. I see.
Yes. Yeah.
If you could design an imaging survey after Rubin, specifically for weak lensing, what would it have that's different than Rubin?
That's a very good question. Biased answer. If I wanted the easy way, I'm probably not supposed to say this, but DS is an easy approach, right? It doesn't have deep data. So we haven't had to face what we're going to face with Rubin yet, which is why I think we can be absolutely sure of our results. So just put an enormous area down and get as much area as possible. Don't try to go super deep, and maximal wavelength coverage. Now that's if you just want S8, but I think if I were to design a Rubin where you get the most information and leaving aside the challenges that we poor lensers have to face, then absolutely go deep, but bring in other overlapping data sets. So near infrared, I think we're going to need a lot more near infrared data to be able to handle Rubin. It'd be quite nice if we could have some X-ray and KSE observations, thanks to ACTS growing alongside as well. And I guess we can see already that we're limited by galaxy formation. And so we have to just start working at that level together to get the maximum amount of information from our data.
Any more questions?
Yeah.
Could you please comment on the Maglim sample? So at some point you had some systematic issues, like I'm wondering if you have resolved those.
Yeah, sure. So I didn't talk about the 3x 2-point analysis too much here. So in DS, so for example, for kids for the 3.2-point analysis, they use BOS and 2D lens, so spectroscopic information that overlaps to get their clustering and their get lensing. In DS, we use a photometric lens sample. We use 2 photometric lens samples. One is called Red Magic, which is a very specific selection of galaxies, but good redshift information. We can do their redshifts well. And then we use a magnitude limited sample called MagLim, where a lot more galaxies, not a specific selection, poorer redshift information. And we decided to use the 2 from the beginning because we could see that we make sure we get the same thing. We actually unblinded our 3x 2-point analysis with the Red Magic sample as our fiducial and had to change afterwards. So we spent 6 months delay after we unblinded. The cosmic share stayed fixed for 6 months. not for a lack of trying. So we unblinded our results, and the red magic results were slightly inconsistent with our cosmic share results. This lens sample was giving us some very strange numbers. We unblinded the Maglim results, and we could see that everything consistency was consistent with the cosmic share. I don't think that that's an observation bias. We required consistency to combine the lensing and the clustering. But the red magic sample, I think that we dug for 6 months what's causing this inconsistency between the red magic and the cosmic share. I think we did everything we possibly could in the cosmic share, and we could see that it was absolutely stable. And it was the red magic. It's not the lensing. It's the clustering that has evidence of systematics and is pulling low. And so we swapped our fiducial to the Maglim sample, which didn't show evidence of these systematics. The red magic sample we've still been digging into even now. We can see that if we relax, so you make a very refined selection to pull out the red magic sample. If we relax that, we don't see the evidence, or we wash out the evidence for these systematics in that selection. We've tried looking at dust, we've tried looking at comparisons to year one, and still we're a bit unsure on what is the systematics in our clustering analysis. And it has big implications for us. So for year 6, we're thinking of just leading with the cosmic share first, where we know that things seem very stable and we have a very good handle on the data, and then thinking about the lenses. What I should say is that doing cosmology with a photometric lens sample is extremely difficult. We have really nice spectroscopic information that's overlapping. It is hard to do galaxy lensing and clustering with photometric redshifts, I think, the key here.
I don't see any questions on Zoom or here, so let's thank Alex again.